Welcome to Circuit Lab, practice number 11. We'll be talking about specialty devices, dependent sources, superposition, and troubleshooting. My name is Mr. Burleson, and as always, you can reach me at geaux15@hotmail.com. Last practice, we talked about multiple sources. Sometimes a circuit has more than one source. Voltage sources are always added in series, and current sources can be added in parallel. Never put a voltage source in parallel or a current source in series. We also talked about Kirchhoffs Voltage Law, which while it is only a Division C concept, is very useful in circuit analysis. So if you're able to understand it in Division B, I would recommend still using it. And basically it's doing a loop around anywhere in a circuit, and all the voltages end up adding up to zero. And so that's how we're able to know that the voltages are the same in a parallel circuit, and how we know the voltages are split in a series circuit. In Kirchhoffs Current Law, also Division C only, but very useful for circuit analysis, is to know that all the current going into a particular node anywhere in a system, with the exception of the output of a operational amplifier, is the key thing to keep in mind is that all the current going in is equal to all the current coming out at any point. So in other words, if the electrons go in, they gotta have someplace to go. But let's talk about switches. Now, a switch is any type of electrical component that can break an electrical circuit or divert it from one conductor to another. It can also close, okay, which means that if it's open, the circuit is open or off. In other words, picture you detaching the two wires. That's open. Closed is where the circuit is connected or shorted. In other words, a very good switch usually has very low resistance, so therefore it appears very much like just a straight wire. Some switches are like a light switch. Normally you'll flip it up and it will stay in that position, and it'll stay either open or closed. Or sometimes you have some switches that are toggle or momentary. Okay, so a toggle switch usually goes between one or two positions and stays in that position, but a momentary switch is like a button, like a starter, if you will, and you press the button, and while the button is pressed, the circuit is closed or on. So my recommendation is, when you do a switch problem, redraw the circuit for every configuration that you're going to test. In other words, it is a completely different circuit when the switches are in one position versus another. Now you look off to the right, and these are all different types of switches. We've got some switches like a mercury switch, which uses the fact that mercury is a conductor, but it's also liquid, and so if it goes to a certain position, it turns on, and if it goes to another position, it turns off. Okay, you've got like light switches, and so it's really important to know about them. But we've got some other ones like the momentary. The red button one down there looks like a momentary type of switch. Okay, and then you've got a rocker switch that, in that case, it looks like one side of your circuit goes into the middle there, and then with a rocker switch you can either turn it to the conducter on the left or the conductor on the right, and you might even have a situation where you leave it and neither side is closed. And then you'll notice you've got little dip switches like the little black box up there, and believe it or not, there are 8 individual switches in that single one switch. So these are just some of the different switches. But most switches generally fall into determining what type of pull and what type of throw they have. So a single pole, single throw switch is a simple on-off switch. This is what most people have seen as light switches. So it's either open or off, or closed or on. A single pole double throw switch is a changeover switch. In other words, if you've got a common coming in, and it'll either go to the left or the right. Okay, now this one is quite often used in three-way switches. Okay, now then you'll have a double pole single throw switch, which is basically like having two single pole single throw switches that are connected. They operated once. So in other words, even though I only flip one switch, it actually connects two separate independent circuits. Okay, now where you see this one quite often, believe it or not, is in a breaker, and occasionally they will attach two breakers together such that when you open it, when you turn it off, it turns both of the breakers off, and then when I close it, it closes both of the breakers. Okay, then you've also got a double pole switch, which basically does the same sort of thing, but it's doing like a single pole double throw, but again, the pole itself. Okay, fuses, and these are a very important safety device. So a fuse basically is a safety device that, as long as you stay under a certain current, okay, it acts like a short. It's like you don't even see it there, okay, which is wonderful. However, to protect the device and to protect the wires and protect everything else, if it goes above a certain current, it has a filament that's specifically designed to burn very quickly. Okay, and so what will happen is that when that fuse burns out, it opens the circuit and it stops whatever type of overcurrent situation you had going on. So this will prevent a short or a high current from damaging other systems, melting wires, causing a fire, etc. Now, when a fuse is burnt out, it is no good and just must be thrown away. You can't reuse a fuse. Now, here's the other thing, is that we're also going to talk about circuit breakers, which are a similar type of device. But the cool thing about a fuse is that it acts much faster. Okay, so in other words, it's usually a better protection. And you see some of the different types of symbols over here, and what some of the different types of fuses might look like. One of the things to keep in mind is that you can usually visually see when a fuse is. Now, a circuit breaker is another safety device, much like a fuse, but what its claim to fame is that when you hit that certain current amount, it trips. In other words, imagine it being like a switch that automatically turns off as soon as too much current starts going through it. Okay, now the cool part is that it just flips the switch. It breaks, if you will, turns off the overcurrent situation, and then you can reset it. And there's no damage. The circuit breaker is still good to go, and life is good. You'll see this quite often used in houses these days. Okay, so in other words, if you put too much of a load on a particular area of the house, and over a short period of time, it bumps up the current, the circuit breaker will go off, and then all of a sudden you'll notice, wait a second, I don't have electricity out of the wall anymore. And so you can reset it very easily. You used to have to buy new fuses. Now, the key thing to keep in mind with a circuit breaker is make sure you fix the problem. And same goes for the fuse. Make sure you fix the problem before replacing the fuse or resetting the circuit breaker. So we're also going to talk a little bit about dependent sources. Now, dependent sources are just like normal sources, except they're dependent on something. So you can have a dependent voltage source, you have a dependent current source. And so you see this quite often used to show an amplifier or some type of very complex circuit. Okay, so these are sources that are dependent upon another element or measurement in a circuit. Okay, a lot of times they'll reference other devices. Okay, so in other words, if I've got in the lower right hand corner V sub reference, okay, and then I might have a gain of my source times A times V sub reference. So that V sub reference could be going into into an amplifier, and the amplifier has a gain of A. Okay, so basically, it operates very similar to a normal type of either a voltage or a current device, but it versus an independent one. So if we look here at an example, okay, these are just some examples I grabbed off of Google really quick. Okay, is that if I've got in the upper right hand corner, the current going through the 100 ohm resistor, I then get a voltage on the right hand side is equal to 150 times that current. Now, here's the thing. You'll notice that it is a voltage source. So even though it's 150 times the current, okay, let's say I have 1 amp going through that 100 ohm resistor, then that's 150 times 1 amp would be equal to 150 volts. Okay. Now, and you look at the upper right one, we have a voltage, and then the current that's being provided is actually based upon the voltage on that one resistor. So you have to solve the equation, if you will, or you have to solve the system and figure out what that voltage is, and then you can figure out what that current is. Now, sometimes they will impact each other and the equations can be very complex. Now, if you look at the lower right hand corner, that's a very complex system. Okay, you'll notice that we have 2 independent voltage sources, we have 2 independent current sources, and then we have a variable voltage source. Okay, and it's got both series and parallel elements. This one, I would actually say, is more complex than anything I have ever given on a test. However, but that just goes to show you how difficult some of these can be. So, how do we solve for dependent source? Okay, with a dependent current source, I usually will use like a KVL, okay, to get my equations, okay? And then by getting a KVL, I get one equation, and then I do a KCL at a couple of nodes, and I get other equations. By combining those equations using algebra 2, I can then solve for I2 and I1. And once I have I1, I can know what my current is at the particular area. Okay. In this particular case, of course I'm going to do a KVL. When I see I only have a single loop, I'll almost always do a KVL, and you'll notice that's actually going to give me just one real variable. And so I can really quickly determine, if you will, using Ohm's law and a single KVL, exactly what Vx should be. Now, superposition. Okay, now superposition is used when you have multiple voltage and current sources. Okay, now keep in mind this is only for independent current and voltage sources. Okay, and what it means is that you can just solve the problem multiple times with just one of those independent voltage sources or independent current sources. And then you take out the other ones, okay, and you basically, if the ones that you take out, the independent voltage sources, you just replace them with a short circuit, okay, and then all the current sources, you replace them with an open circuit. Now you have to do it with each one taken out, and you're only solving for a single independent voltage source and a single independent current source. So if I've got 4 voltage sources, I would have 4 different resolutions. And then what you do is you add them all together. Now, this will not work with dependent sources, and it does not work for power, because power, you remember V squared and I squared being part of our resolutions for power, or part of our equations. So that's why you can't add them together. So what you do is you solve for the voltages, you solve for the currents using the superposition theory, and then once you have the sum totaled voltage and the sum totaled current, well, then you can then derive the total power. Okay. Now for troubleshooting, and this is one of the key things. Here's the Russ Burleson idea of how to troubleshoot something. This is not the only way to troubleshoot. A lot of people have come up with different ways. You find the way that works best for you. But my main way is figure out if it worked previously. If it never worked, it could be a design error. If it worked before, something had to change. In other words, it was working before and all of a sudden it didn't. If it never worked, check the design for any flaws, especially for open and short circuits. Those are usually the most common types of errors that will have occurred. That, and potentially, may not have been powered ever at all. But a lot of times on a test, what they'll do is they'll give you a very obvious problem if you just look for the open or short circuit. Okay, so if it worked before, you check for changes. Is the power connected? Is it plugged in? Number one problem of all time is that it's not plugged in, or it's plugged into an outlet or to a battery that is dead or not working, or the switch is not set up right, so it's not even turned on. The batteries are dead. So these are all the types of things that if you're given a hands-on experiment, check your voltages to make sure it really is turned on. Make sure that it really does have voltage. Make sure the switches really are set up right. Look and see if there's a fuse burned out or a circuit breaker tripped. Okay. Look to see if the light bulb, the resistor, or the motor is burnt out. Okay. A very common thing, let's face it. If you are in your house and your light bulb is working and all of a sudden your light bulb stops working and you flip the switch back and forth, that's what you check on. And then you look up and you say, well, I guess the light bulb is burned out, so you go replace the light bulb. But a lot of times it could be loose. Sometimes the light bulb is loose, sometimes the wiring is loose, sometimes the connectors are loose. And by the way, these are all common things that I might do for my troubleshooting hands-on activity. I may pull one wire out and see if you can figure out which wire was pulled out. I might unscrew the light bulb slightly. Okay? Only after you've checked all the simple stuff. Remember, this is if it was working before, then you look at the design and try to draw it out, and then you try to test it. Okay, now if you used to work and it passed all the tests on the previous slide, you need to look at the design. You need to draw and label it. Okay, try to figure out what the voltage and or resistance should be between nodes. You always measure the voltage in parallel to the elements with a power source on, just like it's running. And compare it to your calculations and see if that's right. You also need to measure the resistance in parallel to the efforts with a power source removed or switched off. Now, be careful, because when you measure resistance, you have to count for both paths between leads. Okay, so you have to look and see if there's any other type of paths. So like what I would say is that when I'm measuring the resistance of a light bulb to make sure that it has a resistance, it's not open, which would indicate that it was burnt out, I'll actually remove the bulb and just measure the bulb all by itself, because if I try to measure it while it's in the circuit, there may be another short or something else that I can't see, and the bulb is burnt out, but there's also a short. Always check the obvious stuff first. Make sure it's plugged in, the battery's not dead, the switch is on, the wire's connecting, nothing's loose. Generally speaking, if something's in series, if one element goes out, they all go out. Okay, so this is like the Christmas lights, where if one light burns out, they all go out. parallel, only the burned out one will go out. Okay, and that's a very common question. Is like, hey, your Christmas lights, they all went out. Is this in series or parallel? Well, it'd be in series. Only one went out. It's probably in parallel. Okay. Remember, you only get voltage if you have both current and resistance. So a short circuit will have both voltage and resistance equal to 0. An open circuit will have a resistance equal to overload 1 or somehow else showing that it's open. Okay, only if there's not another path. So in other words, if I want to measure the resistance on my light bulb, I may have to actually remove that light bulb, or at least remove one of the wires from that light bulb before I can really measure it accurately. The voltage source across a bunch of resistors in parallel with no current will remain the same. And remember, no current equals 0. Okay, the best way to measure resistance is to remove the element being tested and to test it alone. So let's troubleshoot a series circuit. Okay, in the circuit above, all the lights were working but stopped suddenly. What's the obvious thing to check? Okay, what should we measure and how? And what would be the resistance and voltage for each element? If everything else checks out and the voltage at L5 is 10 volts, what's wrong? Okay, so circuit was working, so we know the design was working. They all stopped suddenly. Okay, so we're going to go and we're going to check our certain things. So I'm going to take my voltmeter, I'm going to check and make sure that my 6-volt battery is still working. Well, it is. So my 6-volt battery is still working. Okay, now I'm going to check the voltage across my switch and see if my switch stopped working. No, wait. Maybe I should check something even simpler. Maybe I'm going to look and see if my switch is actually closed. Oh, it is closed, so the system should be working. Now, if I test the voltage and the only thing wrong with it is that the switch is open or somehow the switch is damaged, I'll get 6 volts across that switch. Okay, and so wherever I'm going to get the 6 volts across, that's going to tell me that I've got a problem. Okay, that's where my problem is. But nope, I get 0 because it's closed and it's short. Well, you know what? I'm going to look over at that fuse and see if I burnt out the fuse. Okay, well, I look physically, the fuse looks like it's in place. Physically, the fuse does not look like it's burnt out. Okay, I measure the voltage across there. The voltage is 0, so that means it's acting as a short, so it's not going to be the fuse. Okay, now I also physically look at everything to make sure nothing is loose, no wires are pulled out or anything like that. You know, it could have been my dog ran underneath the Christmas tree and the lights went out. All right, but nope, everything looks good. So I measure the voltage across L1 and it's 0, and I measure the voltage across L2 and it's 0, and I measure the voltage across L3 and it's 0. I measure the voltage across L4 and it's 0, and I measure the voltage across L5 and it's 6 volts. Aha. Now, the reason why it is 6 volts is because since no current is flowing because the circuit is open, that means by KVL, the voltage across all the elements is equal to 0 except for wherever it's open at. So that means that L5 is most likely the one that's burnt out. And I check it, I inspect it, I find out that it is burnt out. Now let's troubleshoot a parallel circuit. In this circuit, all the lights were working, but then stopped suddenly. Okay, wait a second, a parallel circuit where everything stopped working? Well, that means that I may have, you know, that's sort of weird, okay? Because usually if an element burns out, only that element would go bad. So, what are the obvious things to check? Well, the first thing I'm going to check is I'm going to make sure, is it turned on? Okay, because if it all went out, the switch could be open. Okay, the other thing is, I'm going to look at that fuse. Make sure that fuse is working and not burnt out. Okay, so again, I'm going to make sure I still got a 6-volt battery there and make sure the battery didn't die on me. So I'm going to measure it and the battery is giving me 6 volts. I physically inspect everything. Nothing is loose. I'm I measure the switch, and the switch gives me 0 volts, and it looks like it's closed, so we're good there. And I measure the fuse, and I get 6 volts across the fuse. And I physically look at the fuse, and the fuse looks like it's burnt out. Okay, so that means that my fuse burnt out. Now, I could just replace the fuse and fix it. However, what I'm going to do instead is I am going to double check before I replace that fuse. Okay, so it's somewhat open, and I'm going to check each of those light bulbs and make sure none of them are shorted out. Because what may have happened is something shorted out somewhere else, and that is what's causing me to that's what caused my fuse to burn out. Okay, so I check the resistance first between the fuse facing all the lights and the negative terminal of the 6-volt battery. So in other words, I'm checking all 6 light bulbs in parallel. And let's say there's 6 ohm light bulbs, okay? And it comes back 1 ohm. Well, that tells me that pretty much all of those light bulbs are working. Because if it's 6 ohms for each individual light bulb and you got 6 in parallel, that should give me 1 ohm. Okay, if any one of those was shorted, I would have 0. Now, if it came back 0 ohms, I would know I'd have a short, and then I have to take out each light bulb individually and check them. Remember how to argue an illegal question. Okay, always make sure you're reading the question correctly. Make sure that you've listened to all the instructions that the event supervisor is given, and then go to your rules in your binder. Make sure that the event supervisor is using the current rules. Ask for how to implement the question. Don't tell them they're wrong. Just say, raise your hand and say, ma'am, it looks like this is violating rule 3CE. How do I, or 3C 12, how do I remedy that for my division? Okay, or the other thing I might do is I might go, hey, did you mean that this was supposed to be a DC circuit or AC circuit? Because I was looking at the rules, and give the specific rules. Okay, again, ask them for a clarification, because sometimes they may have stated it in a confusing way. So for homework, I want you to update your binder. Now I want you to do level 11 Wheatstone bridges, level 12 dependent sources, level 13 superposition, and level 14 Norton and Thevenin equivalent circuits.